Yeah. Or anyone, if you haven't heard anything, there's not much to follow this, but. Yeah. You can see some window carrying.
The probabilistic models that they use to basically figure out if something's behaving optimally. That was very new to me, and very interesting. Still getting my head around a lot of it, but just the finding a reward function is like one of the big problems. How you actually specify your reward function in a way that doesn't cause really bad behavior unexpectedly. So, the fact that we can learn that is tricky.
Jim, what about you? What's your experience or interest in AI so far? What have you been looking at?
I'm just very interested in the software provided from this section.
Okay.
I think if you watch the documentary on Netflix about AlphaGo, about the match, there's a scene when developer says, oh yeah, it's such a great achievement, but at the end of the day, this program is a simple program. I'm thinking, okay, what is he saying? But actually, after that session last week, looking into this, surely there's some complexity on the neural network training side and managing that. But probably I would agree that it's not so complicated.
Yeah, I had a discussion with someone during our lunch meetup about responsible AI just today, where he thought that with AlphaGo and AlphaZero we've broken this new ground where the machine is now learning how the rules work, and you don't have to teach it anymore and stuff like that. And he didn't know that the sample space was actually the state space was still restricted, and expected there sort of to be this, like, basically in his understanding the learning was like that of a child, and it's not, because the state space is so unlike the world. Like it's a perfectly known MVP. Like there's no hidden information. There's no except for the adversary's future decision, but it's not like so you have these discrete states, discrete actions that you can choose and Monte Carlo research on. And he was expecting to, now that we have AlphaZero, that we could make all sorts of other algorithms, like we could just improve on this compass sentencing or parole recommendation algorithm just using this kind of learning, and the machine could just learn laws because they're rules, right? And I tried to explain to him that the world doesn't easily discotize that way, especially like social life is a lot more complex. And we were it came to an interesting point. We were talking about whether you would actually reach some kind of halting problem, whether, if you tried to have a machine learn all this stuff and discretize all this stuff, whether you would just run out of compute. Okay. Hello. Yeah, that would be very interesting to find out. So it was a more complex problem than we thought. So cool. We have more than one new face. We're definitely making headway. I have to just to start with, I have to make one confession. I did not prepare half as much as I wanted to, because I was off this weekend in Sydney eating awesome hawker food at Hawker Lane, which if you're ever in Sydney, go to Westfield in was it Chatswood? Hawker Lane is wonderful, and I say that as a vegan. But yeah, it was really, really good, but not much time for reinforcement learning. I programmed a little bit of reinforce, and that was that. But I did watch this, trying to get into DTPG, I did watch this amazing lecture, and it, I think, to me at least, helped a lot. So if any of you have read the paper or want to get into the paper, what we could do is, before we get into, you wouldn't be Andrew by any chance, would you?
Oh, yeah.
You are Andrew, fantastic, amazeballs. So before we help Andrew with his problem, we'll go through the DDPG as promised, and then we'll do some brainstorming / troubleshooting on Andrew's report. I haven't had a chance to look at the report yet.
That's okay, that's fine.
Yeah. Okay, Andrew has contacted me. You contacted me on Monday, I think, was it?
Yeah,
Something like that, yeah. So as a last minute thing with regards to a problem that you have with reinforcement learning, I think you wanted to make an environment in
I'm building my first OpenAI gym environment.
Yeah.
I thought it's a toy text one. I thought I'd start something simple.
Yeah.
And it's turned into a monster.
Yeah.
So, because I've got to a point where I go, is this a finite MDP or not? And considering I don't actually, this is my first kind of serious dive into this thing, I'm going, here's my knowledge of maths and Python, and this is kind of going out about here. So I thought,
you've made your own environment for it. This much perfectly.
I need some help.
Yeah.
I don't know.
It will be a great chance to experiment and have a look at reinforcement learning code. So a bit on housekeeping, like there are drinks outside and there's food to not completely feed you irresponsibly. So we have alcoholic and non-alcoholic drinks, as well as the bathrooms are just outside the main door and then at the end of the corridor to the right. It is so terrible, it must be good. The squid and cheese.
I'm a big fan of anything that stinks. So.
Right. So I thought we'd start with this. I'll have to crank my laptop up because unfortunately the audio connection to the TV doesn't work for YouTube, but this should.
The Deep Deterministic Policy Gradient algorithms. Welcome to this 8th reinforcement learning class. After the 7 previous classes, we are now ready to investigate the Deep Deterministic Policy Gradient algorithms, also called DDPG. So what's DDPG? That's reinforcement learning over continuous states and continuous actions. First, a word to say that continuous actions matter a lot because, for instance, this is what is useful when you are doing controlling robotics. So if you want your robot to learn through reinforcement learning, you need to tackle the continuous action problem. And the point is that the action space of a robot like iCube, who has 30 degrees.
Just to interrupt here while we're at it, while we get started. What we've done in the last couple of weeks when we've watched lectures was when there was something unclear, we would just pause and ask the question, which led to some interesting moments like us detecting or like seeing, not understanding what Chelsea Finn was doing, and it turned out later that it was actually a typo and we did get it right from the start. Right, so
it took about 20 minutes, and
then
then we could press play.
Yeah.
Only to then be.
But it still was a good conversation because it led to more understanding of the actual problem.
Yeah.
So if there are any questions with regards to this, just shout.
The freedom is huge. So finding a max of actions which is necessary in reinforcement learning in this huge space is very, very difficult. Actually, if the action space is continuous, you need to solve difficult optimization problems at each time step, which is, of course, very expensive. Actually, this is very expensive if you are looking for the optimum over the whole space. But policy gradient methods and actor-critic methods mitigate this problem by looking for a local optimum. They are called Pont-Triagine methods, in contrast with Bellman methods, which look for an optimal, for a single optimum. And in this class, we will focus particularly on actor-critic methods, keeping policy gradient methods for later on. So let's have a look at the history of actor-critic methods. In the class about model-free reinforcement learning, I presented to you a naive actor-critic algorithm where you just increase the probability of taking actions that led to higher reward than expected. Okay. This naive actor critic algorithm was using a standard gradient descent, also called naive gradient or vanilla gradient descent. Okay. And this paper from Sutton and colleagues in 2000, which is a very important paper where the policy gradient theorem is proposed, has shown that if you are using an actor critic architecture with function approximation in the critic and in the actor, there is a necessary condition between the features of your critic and the feature of your actor, so that your actor critic architecture can learn without bias. Okay, it is shown that if this compatibility condition that I won't explain does not hold, your reinforcement learning or your actor critic algorithm won't converge to the true value but to some biased value. This gave rise to modern actor critic methods with more modern mathematical background, let's say. Then Ian Peters made popular the idea of using the natural gradient rather than the vanilla gradient in modern actor critic architecture, using linear architecture. So, as I told you in the previous class, linear architecture is when you have a weighted sum of features or a linear combination of features. So by combining natural gradient, modern actor critic, and linear architecture, Ian Peters designed the natural actor critic and episodic natural actor critic algorithms. And then later on, Bhatnagar switched from least square methods to incremental method, designing the incremental natural actor critic algorithm. Okay, this was the state of the art in actor critic architecture, in particular for robotics, before 2010, let's say. But in fact, those methods proved largely inefficient for robot control. Okay. The key issues were the following. First, the value function estimation based on linear regression is inaccurate, and the estimation of the critique is crucial for the convergence of the policy. So if you have inaccuracies in your critique, you may have a policy that is strongly suboptimal. So you need to be very accurate in function approximation, and this is what deep learning techniques will bring. Besides, it was proven that tuning these algorithms was difficult. In particular, tuning the step size of gradient descent was difficult. And in deep learning libraries, you can use adaptive gradient descent algorithm which tune the step size by themselves, which makes the issue much easier to solve. So that's the background, and let's say that until 2010, these things were not working properly. This is the context where the deep deterministic policy gradient algorithm that we will focus on in this class was introduced in 2015. Okay. So the paper that introduces it is similar to the Atari paper introducing DQN in Nature. Okay. The idea is that the authors tackled about 30 standard simple control problems, such as the inverted pendulum, the Acrobot, Alchita, etc., and even some car driving problem. And they were able, with the same set of hyperparameters, to learn how to control all these systems at a correct level of performance, either using the state representation, which is supposed to be easier, or using so-called end-to-end policies. So you just give the image of the process to the algorithm, and it's able to learn to control it, as was done in Atari with the pixel of the games. Okay. So again, this was a rather astounding result that people were able to do this, because reinforcement learning with continuous action is considered much more difficult than with discrete actions. So what's DDPG? How is it built? First, it takes a few ideas from DQN that was published 1 year before. So in particular, it reuses the replay buffer shuffling trick that I explained to you in the previous class, and the target queue network trick that I also explained to you when presenting DQN. For The actor-critic approach, it builds on a paper from David Silver and colleagues, which is the deterministic policy gradient algorithm paper. So it's using the deterministic policy gradient based on deep neural network, so it's a deep deterministic policy gradient algorithm. And finally, in the initial paper, they were also using batch normalization, which was a popular improvement at the moment when the DDPG paper was published. But actually, several experimental studies have shown that the importance of batch norm depends on the particular benchmark that you are using. So we cannot conclude that batch norm is a very important aspect of DDPG. So how does DDPG work? First, let's contrast it with DQN.
Actually,
In
can we
DQN, as I
stop
explained
for a
to you in
second?
the previous class.
Yeah.
This discussion about the inconclusiveness of the batch normalization, maybe it's actually substituted by using the two networks, because I think it's about just reducing the variance of the inputs, and that helps stability of the learning. So maybe actually using this target network actually is substitute of this batch normalization. I don't know. What do you think about this random idea?
That's a bold statement.
I think.
Okay, no, just Okay, thank you.
I mean, I don't know. I mean, I just can't see how having target QNet mitigates the problem of high variance in your input data, especially dominance of one particular dimension over the others.
Okay.
It just, I don't know if it's related.
I think it's just this idea of the slow transfer and of the...
Yeah, just Balak averaging, like what we use for target network, just seems to be like stabilizing.
Yeah, but
the
there is like a slow transfer, so yeah. Okay. No.
I always thought that batch normalization is the normalization per layer.
Yeah, that's what I thought too. When I saw this, I thought as you that was the normalization of the weight updates, not the input. But
I thought it was the inputs per layer.
yeah.
So so that's why I think batch normalization is just, I mean, it really depends on what specific architecture you use, like what specific function approximate you use. It's the same thing as that you can't really say which optimizer is the best. It's just like,
Except it's Adam.
well, it isn't. It isn't. Because SGD with momentum actually, for simple problems, actually outperforms Adam. In the cases that I've seen anyway.
Yeah, but then don't do simple problems. It's just.
I have to say, like, if it's a deep neural net, then Adam typically kind of works best. But
Anyone? Person?
Your Q network corresponds to a Q table where you have one neuron per action. Okay? So you give the state and you have one neuron per action. You cannot do that with continuous action because you would need an infinity of neurons in the output layer. So what you rather do is that you have one critic, and that critic only has one neuron for input. So you give as input the state and the action. Contrast it with here where you just have the state. Okay? And the output neuron just gives you what's the Q value of that state and that particular action. So that's nice. You can give some action and some state and see how good it is to perform that action in that state. But how do you compare different actions? For doing this, you need an actor-critic architecture. So close to the critic, you have an actor that takes the state as input and the action as output. And now we'll see how you can train this critic and train this actor so that the actor-critic architecture will converge to an optimal actor and an optimal critic. For the next slides, I will need some formal presentation of the parameters. So the actor will be noted P mu, so the parameters of the actor are mu.
So just from my understanding here, that my inputs A1, A2, and A3 could be something along the lines of the voltage on the gas pedal, say, or like so that it's a continuous action value, and then like the x and y value of the position on the steering wheel, that sort of thing.
Yeah.
That's how they. Yeah. Okay.
So it's basically
It's
R.
real number,
Yeah.
vector of real
Yeah.
numbers.
Yeah. Okay. Yeah. So it's not. Because in the discrete case, we know like actions 1, 2, and 3 or so. But here we have how much we are executing each action. So it's not a probability, it's literally a measure of like how much water you would put in or
So
something like
it's
that.
a range of values.
Yeah.
Effectively.
Yeah.
Does it have then limits, or is it can be limited or unlimited? Because if you say turning a wheel, if you're stuck in degrees, you could say it's 0 to 355 point. No. Or do you actually say
guess
it
that
keeps
depends
going
on-
round and
yeah,
round and round?
that I
from
guess-
say 2000
So typically in optimal control, which I don't know very much about, but I happen to have been reading about this one. It's basically the action space is typically constrained. Like for instance, the example they often give is like I don't know, like a wheel, like your wheels just don't turn any further, or like a rocket, like you just won't behave. You won't have more thrust in a certain direction. That's just all that you have. So there's always some sort of natural limit.
This comes from the problem.
Yeah.
You hope it comes from the problem, or you have to create some kind of boundaries on it.
Yeah.
Mm.
Well. Yeah.
Yeah, and so the trick is how would you incorporate those constraints? A lot of that has to optimal control theory has to do with like how you deal with those constraints.
It sounds to me a little like your action space becomes part of the state space in a way.
No, it's more that it's more like how you combine. Well, it's basically how you model, how you choose to model Q.
Yeah.
As an A.
Yeah. So okay, let me rephrase that. So like let's say your state space is something like your car is somewhere on the road with it at a certain speed and so on. That all defines your state. And so the next state that you're creating, if you will, would be the state where the action is such and such an angle on the gas pedal, say, because that would be like between
I see what you mean. Yeah.
So, and that would give you, how good is that? That would give you that Q value from the critic.
Yeah, I guess that's what. Yeah.
So
sort of a trivial response on part of your state space.
Yeah. Because all the other values could also be continuous, so it's not.
For the Q, the critic, I understand that output will be state and action, and are the action kind of like derived from the state, or they kind of like. Like you mean on the other, like the actor network, how does it integrate?
I think you'll get to that particularly in a second.
The key function is score.
Yeah.
Like how good
Yeah.
that's-
But the actor it doesn't take the action as the input; it will be the output.
Yeah, so it's like the state as the input and the output is the action.
Yeah, that's right.
I try to understand how the actor network.
I think you'll explain that
Oh.
in a second.
But there is a very so there's a very, very big difference of this actor, like this actor specifically, and the actors that we're used to in discrete action spaces. Because in discrete action spaces, it basically just predicts a distribution, a categorical distribution over all the possible discrete actions.
Yeah.
Here it's doing a point estimate.
Yeah,
It's a
and you
very different
couldn't
thing.
softmax this, for example. That would be meaningless.
Well, that as well, but also
Yeah.
that just the fact, so there's no variance, there's no spread in the prediction that's coming from the actor. So really, it is just a point prediction.
Well, that's not necessarily true, right? It's
Well,
just for deterministic actor. But your policy could be stochastic as well, and in that case you would instead of outputting just a
Means.
point and the real point, you output mean and the variance
Yeah.
of it, and then you construct, for example, a normal distribution over these parameters and sample from that.
Yeah.
And also you can even output the mixture of Gaussians.
Yeah.
So you can like
Cool.
you can do whatever you want.
Yeah.
It's just like
Yeah, that is pretty interesting.
This is just sort of like outputting just the mean.
Yeah.
in this case, yeah. Just you can imagine this case like a Gaussian with the just like infinitely small variance, kind of.
Yeah.
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 So I think in this paper it also mentions that this fact that this is deterministic policy, it underpins that it works. So actually has a progress, and the case you described actually is also working now.
Yeah. Any modern approaches like.
So I think they say that the condition of this actually working is the fact that this policy is deterministic, not stochastic. So.
Also, all these conditions seem to be so vague.
Yeah, it's like
they just like so
I will just find it offline.
Yeah.
I don't.
Yeah, exactly. But it's a bit different. It's a bit different.
So soft actor critic is where you take a stochastic, where you've got a stochastic action.
And DPO, for example. DPO, for example, uses mostly stochastic. It depends on the problem as well, right?
I've only seen PPO for for discrete action spaces.
Really?
Yeah.
But it's applicable for continuous
Like the reason
spaces.
continuous
Or with states and actions.
Yeah.
bad for queues and queue learning because you have to take that max. Yeah, how do you do that over continuous? It's like a whole problem in itself.
Yeah.
But like for policy gradients, not really an issue. You don't take max.
Yeah.
Yeah, just mostly based on the assumption of the monotonical, of how monotonical your Q function is. I mean, optimal one, right? If you believe that it's quite smooth, then you can model it within continuous space and it all does well. Yeah. But
I also quite like how he's displayed like the critic has like 1 million neurons to do its like massive state space, and all the actor has to do is it can use less neurons than it has, state inputs. That's fine. It just has to predict the queries for a couple of actions. To me, that seems like the more difficult part. I don't know.
Yeah,
But,
I think usually these things actually share part of their.
That course, yeah, it was.
Maybe not here because
maybe that's
actually
still
they
come
can't
later.
do that here, of course, because.
Yeah, it might come later. I'm not sure. Maybe we'll just look ahead and see, or like we'll look further and see what this one is going.
Okay. And the critique, the parameters are theta, but that's again parameters, the weights and the biases of neural networks. And again, you will see that all the updates that are performed in this architecture are based on stochastic gradient descent. So you can use all the standard deep learning libraries like TensorFlow, PyTorch, etc., and make profit of adaptive gradient descent techniques, which tune the step size so that you don't have to deal with that. So first, how do you train the critique? This is exactly as in DQN. So I explained to you how it was done in DQN. So that's the same idea. The equations are a little different because the input is a little different and the output is a little different. But again, you want to minimize the reward prediction error or the temporal difference error so that it goes down to 0. Okay. And for doing so, you take a mini match of n samples. You compute the target value here as was done in DQN, and you minimize the squared loss, which corresponds to the distance between your desired value and the output of your network. You can see that I have put in red some aspects that I will explain later, that instead of using the action in the samples, you are using the action that the actor is proposing for that particular sample, and I will explain you why later on. So this was for training the critic. Now, how do you train the actor? The idea is based on the deterministic policy gradient theorem that was proposed by David Silver, which can be stated with that particular equation. I won't focus on the equation, I will rather try to present the intuition. The intuition is the following. Assume you are in a particular state. Your actor is proposing a particular action. You can evaluate this action through your critic. Now, if you want to improve your action, what you can do is take a slightly different action and see whether the Q value is a little higher or a little lower. If it's a little higher, then you should change your action towards this new action, which is better. So in fact, what you can see is that by taking the gradient of the Q value with respect to the action, which means you consider whether taking a different action is better or worse. So in taking this gradient, will let you know how to evolve your actor in the right direction. Okay. So in practice, you take the state, you compute the action, you put the action here and the state here, and you compute the Q value. You propagate the gradient of the Q value with respect to these actions, and this gives you an error, and then you train your actor with this error as a loss function, and your actor will improve provided that your critique is accurate enough. So in the beginning, you need to train your critique faster than your actor so that your critique gets accurate, and then your actor will get more and more optimal as your critique is improving. That's the general idea. One point is the following: how do you compute the gradient of the critique with respect to the action? What you can do with standard backpropagation algorithm is compute the gradient of some error with respect to the weights. But actually, if you look at the equations of a neural network, the weights and the input are playing a symmetric role. So in fact, in standard deep learning libraries, you can compute the gradient either with respect to the weights or with respect to the inputs as you want. Okay? And in practice, here you will just take the gradient with respect to the input which correspond to actions. And that's it. And let me say that those ideas of this way to improve the actor this way of computing the gradient with respect to the actions was already present in a previous paper from Reid Miller, which is an author of the DDPG algorithm. Okay, that's the general idea. I did not mention that for having the critique converge, you also use the same tricks as in DQN. So you use replay buffer shuffling and you use a target network. By the way, for the target network, in DQN we were updating the target network each, for instance, 5,000 time steps. With DDPG is what it was shown, and I will come back to that later, that it's a better idea to have the target network track the current network or vice versa with some decay parameter which is called tau and which needs to be tuned. I will come back to that later on. So now that we have some picture of how DDPG is working, let's look more closely. I told you that there is some difference with respect to DQN, which is that the action that we are using corresponds to the action of the actor. Why is this? In fact, we have to come back to what I explained to you about actor critique methods in the discrete state and action case. Okay, we are using a replay buffer. From that replay buffer, we take some samples. From the samples, we can update the critique as usual. But for updating the critique, you need to compute the gradient with respect to the actions corresponding to the actions that the actor is taking. So here you are taking the gradient with the actions of the actor and not the actions that is put here into the sample to perform this computation. But also to compute the target value to update your critique, you also need to take the action of the actor here. So you need the action of the actor. So one may think that this corresponds to an on-policy method rather than an off-policy method. In fact, it's not, because this is a standard actor critique architecture, and as we have seen, an actor critique architecture can work in an off-policy manner, okay? But as we have seen, convergence is rather fragile, because if you are not lucky in the beginning, your actor will stay poor, so the updates of your critique will be poor too, and you may, for a long time, not converge towards a good policy. So, Deep Deterministic Policy Gradients, so DDPG, is rather fragile in the sense that you need a lot of hyperparameter tuning so that it converges to something satisfactory, which is clearly the main weakness of this algorithm. One point to say that what is nice with an actor critique architecture is that the different parts, the critique and the actor, are rather separate and could be updated independently from each other. So you can update your critique at a certain pace, okay, and update your actor at a different pace. So updating the critique and the actor can be done in parallel, with different computational resources.
Yeah, I was a bit confused about that when I first watched it as well. How is that different from a target network used for DQN, where you have, because this sounded to me like you would have a staggered network of actors, or they would train in parallel and then you would take the average? How would you, or are there different ways of doing this? How would,
could you say again?
okay, so I'm trying to understand what exactly the difference is here between using several actors or several critics and using a target network that you then update at certain intervals. Because would you just train several actors and take the best performing one to get a less fragile convergence?
In vanilla DTPG.
Sorry?
In vanilla DTPG.
Yeah.
No, you just have three nets. In vanilla one you have just 3 nets.
Yeah.
The one is your QNet.
Yeah.
Second one is your target QNet,
Yeah.
which is basically which you update using your QNet with some kind of product averaging function. For
Every 5
example,
epochs or 500 epochs.
no, it's at each time step you just copy weights from your QNet into your Q target net
so you
with some
partially upgrade it.
with some kind of discount factor.
Yeah.
Oh,
That's
okay.
it. That's
Yeah.
it. Like just averaging it over time, kind of.
Mm-hmm.
And the last one is your actor. That's it.
Yeah.
Policy, and you have just one.
Yeah.
But also you could implement like some. I mean, in some cases, you're not restricted to have just one actor. You could use a couple.
Yeah.
But
And they evolve in parallel because they have randomly initialized starting states, so they'll be slightly different over time, right?
well, it's like almost A3C and A2C and all these algorithms. There are different implementations.
Yeah.
There are some asynchronous ones when your policies are allowed to diverge from each other, but then at some point you kind of stop them and say, okay, guys, now it's time to, to come along and decide what's the best course of actions.
Yeah.
And another one, when everything is synchronous, in that case you update your policies at each episode. With the same update, so they don't diverge from each other.
Yeah.
The only benefit is just to gather more experience in parallel.
Yeah. So you run through more samples in parallel.
Yeah, from like parallel environments.
Yeah.
With the A3C.
Yeah. So how do you then update? I haven't read the A3C paper that well yet. So how do you then update to the optimal policy, if you will, from multiple actors? How do you get, if you wanted to?
You just share the one critic. You just put all the experiences, all the samples in your replay buffer, and then sample from there.
Yeah.
And update your critic.
Yeah.
And then you just plug it into your equation for the policy update, and that's it.
Oh, so that's to train your critic with multiple actors. So then you basically make a super critic, and then that makes your actor better. A single actor that then becomes the executing.
Each actor is more like it's more like one of the parallel batches.
Yeah.
So actors are in the training sense are just sort of policy updaters.
Yeah.
So that's all that they do. And then one thing that's very different in the A2C or A3C is there you use just the state value function, and here you have your state action value function. So that means that you don't have to calculate the sort of the TD error. You can just calculate the advantage directly. So it's a different ways of just sort of calculating the same thing, which is the advantage.
Yeah.
But I think other than that, the thing that I don't really understand is like why it has to be deterministic. I don't understand. But that's what they say. So many approaches in reinforcement learning that uses the recursive relation, and then they should. Well, this is in the paper. So they show the Bellman equation, and then they say if the target policy is deterministic, we can you can basically just take as your action the point estimate coming from your actor, from your policy. and then I think that's what they use to then sort of propagate the error back from, like, through the value back through to the input of the actor or something. That's the thing that's not clear to me.
I don't remember the details.
I think the idea, why it's this way, it's sort of enable this offline learning, and this is the condition of the neural network working, because probably if you were using it like learning step by step, it wouldn't work, as this case with those target and Q network. Yeah, I think that's the reason.
So it's not that you're propagating the errors back through, like from the value network to the policy network. I thought
that's what you do.
Yeah. So then that's the reason why it has to be deterministic, I think.
Honestly, no. You still can do backprop, or even if your policy is stochastic.
Yeah, but it
with
makes it harder.
the so-called reparameterization trick.
Yeah.
But
not using the reparameterization.
Yeah, they
trick,
do
right?
not, because they.
No, but with the I thought reparameterization trick is exactly the thing that kills that the sort of the backpropagatable.
No, it allows you to do backprop. If your policy outputs a stochastic element, which is, for example, mean variance, and then you sample from that mean and variance distribution, how can you do backprop from the sampling procedure kills backprop. Reparameterization
and then
allows you to move this sampling stochastic procedure a little bit aside, so that your mean and variance are not
affected. Your mean and variance can actually be adjusted by the.
Yeah.
Yeah. Right.
Yeah.
Okay.
But that's a different story. Honestly, I don't know about this proof of convergence for deterministic case. I don't know. Like, I've read so many papers about ML so far, and it seems like all of them are just like, all the proofs are made under so many different vague assumptions, honestly. So, that this just formal provement of just that it works, so it doesn't, I don't know. It always just depends if you're lucky enough or not to train the net.
I think it's probably more a statement of like our method works when you do this. I think it's not much more than that.
I think the way it's all been set up, like, you know, they had the deterministic policy gradients and then like the deep method, and that's what they were testing out.
Yeah.
And whatever happened later on, like whether stochasticity had it, like they weren't really looking at that. I don't know.
Yeah, but now it's more common to use stochastic elements in ecology somehow.
Yeah. Because it's also a little bit dated in that way. That maybe it wasn't that clear then. Well, actually, it's not dated. 2 years old. Yeah.
No. It's not 4, yeah?
This
it's
is
to 2015.
16.
16.
I still have
Well,
that.
see, already outdated.
Sorry, I'm still not 100% clear on how the actor updates the critic, and then I was looking at these these guys over here. This looks like they update they don't update the actors per se for a while, right? They do steps and they do things and they do steps and they do things, and then they constantly update the critic here. Yeah, they constantly do things on the critic, but they don't check in with the critic all the time. Is that what this means? I'm not.
I don't know what that is.
I'm a bit fuzzy on how this.
I think that's another algorithm, right?
Yeah, but shouldn't it be the same? Like in principle, like this is just parallelization of multiple actors with a single critic. So shouldn't that be basically the same, but with? See you next time. Shouldn't that be the same as with one critic? Just if you leave out all the other actors? Like it seems to me
I
like.
can't see what are the colors.
So light blue is
the
forward pass.
Forward pass, backward pass is dark blue, and grey is environment step.
Ah.
Yeah, so it looks to me like here in the A2C case, in the batched A2C case, they are having 4 actors, and only actor 1 is actually constantly doing something. Yeah, although I don't understand if they do forward pass But they do not
It's
take
like, you know, the actor one made it to the end of the episode and the rest of them died early on.
Yeah, kind of.
And
Yeah.
Wait until everyone's finished and then go again.
Yeah.
I don't know.
But it seems the same kind of like here, like where this is like this thing goes like this waits like 3 rounds to do something. I don't understand how this is meant to work.
Well, no, I mean, my guess is that on the x-axis is more like time.
Yeah.
It's time, right?
Yeah.
So probably it just means that, for example, actor 1 makes a step in, let's say, 1 second, and actor 1 somehow it takes him like 3, 4, 5 seconds to proceed to the next step. For example, of the just because of the dynamics complexity, you know. So if you use integration, for example, in your environment, you like the time you spend on the step on each particular step might vary a lot.
I mean, I
But the one
think
under
parallelization is cool, but it's not really important for the algorithm.
So maybe this start time differentiation, maybe it's to get some differentiation of the updates. So they are not, if like a couple of actors follow the same path, the update will be like correlated. Maybe that's, I don't know, maybe some, I don't know.
Yeah, but what's funny about this asynchronous one on the right hand side? So basically, like you can see that the one on the left is A to C, right? Synchronous advantage actor critic, and the one on the right, I don't know, it's called impala, but it's essentially A3C, asynchronous advantage actor critic.
Just distributed.
Yeah. And it's been shown that asynchronous one doesn't do much better job than the synchronous one. But it's way more complicated.
All right, I think I understand. I think I now understand what you were saying. So here, that's the asynchronous part. Like it doesn't allow, or it doesn't need the same amount of time for each actor to come to its decision. But they all take 4 decisions. They're all passed, like let's say, you know, S0 to S3. They're all given 4 points of decision, and however long it takes them to make them whatever. Yeah. And so this guy here does 4 updates. Yeah. So whenever they're available, it does these updates, and the last update that it does is this one here, I guess.
Yeah.
With all of this stuff. Yeah. Okay. So and I guess they'll just be saved somewhere in between whatever. Yeah. So and so these are all available here. This is there, but this is where this takes. That's a little bit more fast. Okay. I guess. Yeah. Yeah, but that now makes sense to me. So it does actually, it just collects the responses from all these actors, and so the maximum time that it takes to do all of it is the time that it takes all the actors to take all the actions.
Yes.
That makes sense. All right. Okay. Yeah, and so all the actors are given all situations, and it just waits for all of them to finish. That makes sense. Cool. Okay. Anyone else?
Do they combine all the actors and then make a decision, or you just choose every time you register?
I think the way I understand this here is it would just pick 8 different it picks 4 different states and hands these 4 different states to the 8 different actors. And then once they're all done, kind of like a really nice teacher in school waiting until all the students are finished, it does all its updates, or like it can then do the final update when the final thing is done. Does that make sense? It uses all the information from all the actors across the 4 states.
Actually, you can see in the literature that using several actors is a good idea, and I will explain you why later on. But you may use several actors, several critics, several replay buffers, etc. And there is a lot of work in the standard, like in the current reinforcement learning literature, particularly in good companies, in big companies where they have a lot of engineers, where they can perform all these designed all these parallel architectures to show that using parallel architecture you can improve the speed of convergence of these algorithms a lot. A word about exploration. This is a very hot topic, so I could make a whole class about exploration. Here I will just focus on one aspect that is important for DTPG, but this is a lot important. In the standard DTPG algorithm, they are just adding, okay, the actor is taking an action, and then you add some exploration noise to that action, using either some standard Gaussian noise or using an Ornstein-Uhlenbeck. So that's a correlating noise process where the noise at the next step depends on the noise at the previous step. In the original DDPG paper, the authors were proposing this, and in fact, later on, it was shown that using an OU noise process or a Gaussian noise process is quite similar. Later on, it was shown that using this action perturbation scheme, where you just add some perturbation to the action, is not the best you can do. It is a better idea to rather perturb directly the weights of your actors. So if you are doing so, okay, let's focus on the difference. So these work were proposed simultaneously by Plappert and by Fortunato in the two following papers. If you add noise just to the action, this will change the action you will take, so this will change the content of your replay buffer, and so this may influence the way your critic will learn something, and finally this will influence the parameters of your actors. But if you are not lucky, a change here may not change a lot your critic and may not change your actor at all. Whereas if you are using action perturbation, if you are using parameter perturbation, you are directly moving in the space of parameters of your actor. So you have more chance to find a nice set of parameters by moving directly here rather than moving here and then here and then here.
Yeah.
Okay. So it's a better idea to explore this.
By just
and another point is that, as I told you, it's a better idea to use several.
So it's basically, that sounds like, what it sounds like to me is basically making it stochastic, but like by changing the network parameters instead of sort of modeling the actual distribution of actions.
Yes.
Yeah.
Hitting flipper. What are they calling it? In English? I can't remember.
I don't know.
Pinball. Yeah,
that's right.
Just like
Because I would say the same thing.
Yeah.
So
Yeah, that's interesting though, and it's kind of like the same thing as using multiple actors, but in a more targeted way, I guess, right? Because you can have one actor that you constantly poke and shake up, and that be the same thing, I guess, in a.
Well, you immediately have the sort of the good result in your space of parameters, so you don't have to search for it longer than.
Yeah.
That's a good thing.
Sorry.
Is it right to say that if you perturb the actual action, you might not? It's what you were saying, that if you perturb the action, your policy might not actually. That might not be actually close to your actual policy, but if you perturb the weight, that's closer to your policy.
Yeah.
Is it? I guess you could say perturb the policy if you do that.
Yeah.
Yeah.
That's basically what this is. Or the function approximate.
But then that's just heuristics, right? So there is no guarantee that shuffling your weights rather than actions would make a better job for you. It just has been shown in practice that it works a little bit better. That's it.
So
I think what would better if you actually were to model the uncertainty directly.
Well, that's called Bayesian approach.
Yeah, exactly.
And that's the whole like big thing as well.
Yeah, I guess was that after this?
It's just in parallel.
Right.
Yeah, I haven't seen many connections between RL and Bayesian.
Right.
But yeah, it's cool. I'm trying to
I
incorporate
think
it.
it's also DeepMind people who did the sort of the simple application of where you each weight doesn't just have the mean weight, but also the variance of the weight.
It has a distribution
So
of the weights, yeah.
Yeah, exactly.
Yeah, and the first one was
in terms of
introduced.
the number of parameters is just times 2. So that's pretty good.
Yeah.
So you just assume that so the prior on all of the weights is a Gaussian basically.
Yes.
So you just
But you
assume-
sample from there every time. So the magnitude of your data set and amount of forward passes has like
that definitely
it's
grows,
bigger,
yeah.
like 100 times or something like that.
Yeah.
Yeah, it's cool.
Would that change the way you have to backprop?
Well, so with
Would you
this
have to-
reparameterization trick, you can actually just backpropagate even through stochastic nodes.
Or even there are two simpler approaches. The first one was first introduced in in the original operational OK code paper, and what the guy did there, he basically injected a dropout to each node, each weight of the neural net. Dropout, right? Like
Yeah.
the one we use all the time, but just
Yeah.
like
Which is just a stochastic adjustment. Right?
Yeah,
So
but
just a-
the way dropout works, we don't use it. We kinda throw it out in our backdrop, right? But in here, you just apply dropout every single time. You do your forward pass, backward. Doesn't make any sense, right? Okay, whatever. And the second one is just to initialize, just to get, let's say, 20 neural nets with the different initialization techniques, and that's it. And then just average them and do backprop through all of them, and that's also somehow can give you some sort of distributions, and it's just way easier. Sounds like it.
Sounds like we should definitely have a presentation or a paper or something on the topic, because that would be very interesting.
I think just going back to this perturbation in a weight space, I think we looked at one paper that was doing that. I think there was not policy optimization, but the weight of the network optimization. I don't remember exactly, but there was such a thing.
I don't remember.
Okay, but yeah, there was one paper that looked at that.
Actors simultaneously, because these several actors will explore different parts of the actor space simultaneously. So you get a better chance to find a nice place to get an efficient policy. And if you get an efficient policy, then you get nice samples with a lot of reward in your replay buffer, and your critique will improve faster, and then you will get better actors, and so on and so on. So there is a very positive feedback loop, which makes it that using several actors is an excellent idea for exploration. There is much more to say about exploration. There are many interesting exploration techniques at the moment, but I cannot go into that in the context of this introductory class. A word to say that, as I told you, DDPG is a very sensitive algorithm where you need to tune hyperparameters. So a few examples about this, and this is not the whole story about all these parameters, this is just to show you what you can do. For instance, I told you that for updating the target and Q network, you need some hyperparameter which is called tau, which tells you how often you update your target network if tau is greater than 1, or at which rate you update it if tau is smaller than 1. And actually, if tau is exactly 1, this is you update it at each time step, so this is exactly as if you had no target network at all. And for instance, we performed a study in a benchmark called continuous mountain car, using different values of tau, and we could find that in that particular case, the optimal value of tau was smaller than 1, okay, consistently with what the DDPG authors found. Okay. But the point is that if we were using a different benchmark, definitely we would find a different value for tau. So it's hard to get any general message from these hyperparameter tunings. The same about Huber loss. Huber loss was something that was, how do you say this? That was tried by many people at some point. So the idea is that for tuning, for learning with a neural network, in general, you use a squared loss. And it was found in some supervised learning context that using the Huber loss, which is something which is more linear than quadratic, where you have a parameter delta that tells you how far you are from quadratic, may be advantageous. So we also made a study to see whether using Huber loss was a good idea or not. And actually the study was completely inconclusive because using the Huber loss or not is a good idea depending on the problem you are tackling. So again, if you change the benchmark, you will find that using the Huber loss is good, or you will find that it's not good. In our particular case, we found that using the Huber loss was not providing any advantage, so we just removed it. So the general message is that tuning these hyperparameters is difficult and clearly dependent on the problem, which is a rather bad situation. So a general good idea is to start from the baseline codes which are provided by OpenAI at that particular address, and then tune the, so they provide standard hyperparameter tuning, and then when you want to play with your particular application, you should move away from the standard parameters, but studying slowly how to change these parameters depending on your problem. A few other concepts that were used together with DDPG. For instance, there is the concept of a gradient inverter. So for instance, if the domains of your parameter is bounded, for instance, if you have limited actions, you cannot have actions greater than 1 or smaller than -1, which is the case, for instance, in continuous Monte-Carlo. The gradient may push your weights or your actions beyond the boundaries. And if you do so, the gradient will continue if you just cut the values so that they just go beyond the boundaries. The gradient will continue pushing, and this will be completely inefficient. To avoid this, some people were using, for instance, a hyperbolic tangent function, which squashes the gradient to stay within the boundaries. But, for instance, Oaksness, Esch, and Stone found that rather inverting the gradient when you are beyond the bounds is a better idea, and they found that it was more efficient. We found this also to be efficient in continuous Monte-Carlo and Alphita, but again, we cannot conclude that it is always a good idea to use the gradient inverter. Another point which is also well known is related to the overestimation bias that I've told you about during class 6. Okay. You have here an illustration of the fact that this is the value, the average value of the critique. And if you know the problem, which is in that particular case continuous Monte-Carlo, you know that the average value of the critique should be around 60. So you can see that during learning, the overestimation bias makes it that the average value of the critique is going much higher than what it should due to the propagation of the due to the max operator. So one simple idea to improve over this situation, which also generates some divergent behaviors, consists in clipping the target clipping so that the value won't go above the value that it should go. So for instance, if you know the maximum reward, you can clip your critique so that its average value won't go above the maximum reward that it should take. If you are doing so, you will improve the convergence behavior of DDPG. But the point is that if you do so, you are using some knowledge about your application that you may not be willing to use because it's not always the case that you know that that's maximum reward. Okay, and there was a recent paper which is here, okay, which proposes a new algorithm called TD3, which contains several nice ideas, but one consists in having two critics, and in order to prevent overestimation, you'd always consider the mean between the two critics, and you propagate this mean rather than the standard max. So if you do so, you will avoid a lot of overestimation. Actually, the author told me that if you use free critics, then you...
Is it similar to this double Q learning? I mean, the problem and the solution?
I don't know what this does, to be honest.
What the target action? What is it?
No, I just was wondering if this is similar problem and solution to this double Q learning?
Oh, you mean the min?
Yeah, yeah. Or that it had two critics and...
Now that I thought the double Q had this
Like a-
benefit
yeah,
that
yeah,
you
yeah.
get more stable because you have this sort of cross-pollination between the two independent networks, whereas here they don't touch at all, right? You just take the minimum.
Oh, okay.
So maybe the now you're right, because they do touch through the actor if you have only, I guess.
Oh, take the min of the two, of course.
Yeah.
Oh, sorry, I didn't really get it. Yeah. Well, yeah.
Vaguely. Okay.
Yeah. So
Vaguely
take the
similar.
pessimistic critic, I guess.
Yeah.
Yeah.
But they know, but they do this because they know it will overestimate. So.
Yeah.
Yeah.
I'm a bit surprised that target clipping helps, because I would have thought, like, if you tell it can't get better than this, then it could just it'll just always range around that value, wouldn't it? Like
Well, no, not necessarily, because your gradients will just overshoot. Like, one of the things that well, at least I mean, I guess a few days ago when I was doing the alpha zero thing. So the natural, so like the rewards is plus or minus 1. I would say just use the logistic loss, but I decided to stick to the paper, so and they use Huber loss.
Yeah.
So you do Huber, and initially, so eventually, that's what you see as well. So eventually, the rewards sort of hover around where they should be.
Yeah.
But initially, they kind of overshoot, because that's just a property of the Huber loss. Like, you just kind of shoot too far, and then you slowly roll back to where you should be. But in the meantime, you may have just killed exploration, right?
Oh,
because
I see.
because the critic is the person that or the thing that is dictating where the updates go.
Yeah. Okay.
So it's
yeah.
I don't know. But I don't like this though. This clipping. You use a proper loss function.
It feels like cheating. That's what I can't really, because the moment, and maybe that's what he was referring to. Like, if you know that your function is meant to go around 60, then that's fine to clip there, I guess.
Yeah.
But if you're thinking, I might overestimate, I better limit this at 100, and then your optimal loss, your optimal Q is at 200, say.
Yeah.
Then you just completely shot yourself in the foot.
Yeah.
You're not going to see anything.
Like another
That's
thing
like
in Sutton and Bartow, what they propose, and I see no one do in actual real life, is where you just keep track of the average reward. So where you just offset the average reward that you see.
Could that be because of sparse rewards and it not being popular?
I don't know. I don't know.
Oh, this concept itself, it wasn't used elsewhere.
I haven't seen it. Probably people are using it, but so I'm not gonna say no one does it. But this idea that with every update, instead of taking this RT every time, you keep track of some sort of mean R, and then you feed this into your algorithms instead. And this is just like the stupidest sort of estimate, which is just the average. But I don't see anyone do that, and that would kind of solve this, I think.
That is, I think we had spoken about that before, where you would basically, similar to a multi-arm banded approach, where you just keep track of your reward. In this, like you said, this is the simplest way.
I mean, you just alleviate having to learn this. Because
Shall we go through the last more than a half-ish, 2 minutes of this, because it matched with the last half hour, and then we hand over to Andrew and discuss.
Start having some underestimation. So again, this is very empirical and maybe problem dependent. But it's nice because having two critics does not require that you use some problem-related knowledge So it's better. It's a better idea. By the way, the TD3 paper also provides a few additional mechanisms. For instance, it justifies they also use a target actor, which shows that they show that you need a slow update of the policy so as to avoid divergence. A final word to say that all these algorithms, DQN, DDPG, etc., are using a replay buffer, and I told you that replay buffer management is an issue. So I like very much this very recent paper from a few colleagues where they take two different benchmarks. One is a simple pendulum task, and the other one is a magnetic manipulation task where you want to have an iron ball move at a particular place by playing with magnets. And they show that with two different replay buffer management policy, they get contradictory results depending on the two benchmarks. So in the pendulum swing up, you should keep the replay buffer as big as possible and use a first in, first out methodology. Also, you need a full replay buffer and keep everything. And if you use the first in, first out methodology, you are not as good. And in the second benchmark, you get exactly the opposite results. So again, replay buffer management depends on the problem, and the best strategy will depend on your problem, so you need to tune that. So that's the general message about DDPG, that this is a rather simple algorithm which is able to achieve many things and which is quite sample efficient because it uses a replay buffer. But actually it is quite sensitive to the context you are using it, and you need to tune the hyperparameters if you want it to work properly. And that's it for that class, and thank you for listening.
I'll send you the link for the invite on Slack, and then you can present on the.
Okay. Is there a Wi-Fi network I can connect to?
Yes, there is.
Should probably need it, but just I won't get it. Or I can just. Oh, you're using Apple TV.
Let me just do this here.
That's in the continuing control, so not continuous, but continuing.
That's Meetup.
So I think probably chapter.
How do I get to the Wi-Fi?
The Wi-Fi is mantle guest, and the password is mantle 20.
So where they take the
Average reward.
I don't think so.
Thing that, yeah, the average reward. So he says like
ANTL 2019.
this idea of taking this.
Which will of course now change now that I've
discount
said it on the
into the
internet.
future.
I think you have to be in the building to use it, so I'm not really
So
sure.
what he's saying is, if you have incomplete information,
Just let you know, Apple is not my
so if you take this,
operating environment, so you might.
It's all Google. It should be all.
Yeah, how do I
in this internet.
Yeah. You just navigate to the website and then click on join meetup and present
Well,
now.
like gamma times maybe the next one, or you can do end step. So what he's saying is that if you've got incomplete information about the state, these things don't act as expected.
Do you have
so
the
in particular, so he
link
comes
in
up
the
with a very contrived example.
Do you have the link?
Basically, what you end up doing is you're taking just the full sum of all of the gammas.
Yeah.
I'm not sure I have.
Which is
Because I
basically
did
just the
everything through my
geometric
PC
series,
at home
right?
Oh, I see.
So,
Okay.
The problem is
you're
that
stuck on
then
the phone,
this
maybe?
just
Otherwise I'll
becomes
just
an overall
let me see, I'll
factor.
just see if I can.
You just have one overall
Okay.
factor, so it's unimportant.
It's just a couple
And that's
of
assuming
just put it in.
complete that there's absolutely no difference between states, which is also not true. But this is sort of how he illustrates why he says this is not the good way to do it. Instead, what you should do, he says, is take your R's and then replace them. So wherever you have R's, you just replace them by some average, where these are updated as basically with
all state
exponential
actions.
Hmm?
So what this means is update all state and actions.
Just over all observations.
Like whatever you see, you just incorporate it.
Yeah, yeah. And then it's stupid, but if you keep it rigid enough, so for instance, like if you keep no, I don't think that maybe let's use beta, so beta times the previous one plus 1 minus beta times the new
Otherwise, I
observation.
can quickly open your repo. Because you sent me the link
Then,
already.
as long as B
but
is sort of big, let's say, like that, then this is a pretty decent, sort of stable enough thing to use. But yeah, I don't know. I just don't find it convincing, and it seems that no one does it either. So.
I don't see what's really bad though.
Yeah, but as long as it's all the same for everything, right?
Yeah.
As long as you don't update it that hard, I think it's fine. Yeah.
It's just more like a baseline. So if
Yeah,
all
exactly.
your rewards like above 100,
Yeah.
what just like
And you allow your baseline to slowly move. But not
subtract 100 from all of them and
Yeah.
kind of stabilize your gradients overall.
Exactly.
So it's within some decent range.
Yeah, and it's also like if you find a hyperparameter that works in that case, it will also work in other cases.
Maybe you don't do this because normally you do have access to your reward function and you can do reward shaping. So you can control your rewards
You make
over
that
there.
like in sort of centered around 0. Yeah, maybe.
For example, you is +1 minus 1. Why would you do?
Yeah.
Why would you subtract 0? Right?
Yeah.
It's already set.
Yeah. Well, so you might want to do it. So there must be a reason why not to do it, because David Silver is like the Sutton protege, right?
Yeah.
So in their case, what they say is that with every reward that you get, so they just clip it at ±1 for all of the Atari games.
Oh, really?
Yeah. And then later on they use Uberlos, which makes it a bit more robust, and you don't really care about it. But I still think it's not a bad idea. I mean, why not? I just don't see
So I think
anyone do it.
also, I'm not sure how this is related, but I remember last summer reading that the concept of advantage was also to somewhat limit the variance of the.
Yeah, it's a similar idea. But that's in the space of different
It asked me to enter a name for it.
oh, I see.
and
Okay.
this is in the direction
There you
of
Somebody
go.
let me, somebody will let me.
Yep.
any
You are.
observation.
Hey, okay, cool. So, okay.
Yep.
Cool, right. So, hello everyone, including anybody who's on the internet.
We have one viewer on the
One
internet.
viewer. Hello, one viewer on the internet.
Hello, Eva, Nico, Patrick.
Yeah.
So you don't count, though?
Yeah. So just to give you a bit of background.
As a viewer? You don't count as a viewer?
No, this doesn't count. This is just a camera control.
Oh, okay.
So my name's Andrew Buttery. I started getting interested in machine learning and stuff around late 2017. I spent most of last year just self-educating via Udemy and so on. Got to the point where I wrote just a simple credit card classifier so I could keep track of where my expenses were going using a naive Bayes kind of thing. So something really basic, but got inspired enough that because my work is going to be heading down this way, that I need to understand a bit more about it. So I'm now doing a Masters of Data Science at RMIT, so I just finished my first semester there. And I have a break of 3 weeks, and during that time I started seeing a lot of the open AI stuff and thought, that's really cool. So for my break, I thought, well, how about I try building some kind of reinforcement learning type thing with an ultimate goal to build, spider robots and stuff. But hey, that's kind of that's way down the track. So I obviously have a huge learning curve in front of me, considering I understood about 20% of the last hour. So that's my background. So what I chose to do to build an OpenAI environment, and I decided that I was going to have a look at something which I discovered when I was very, very young, which is a game from a long, long time ago called Chase. It's in here. It's basically a text game. But yes, so some of you who are very old, I generally get told that I am younger than I look. Sorry, I look younger than I am. But this is something that I actually played with when I was very, very young, when I was doing my first set of programming. And it's all basic, and it's all pretty horrible nowadays compared to what you would do. But there is a game in here, which I'll get to in just a second, because I don't know where page down is on my Mac, because it's not my native environment, so apologies in advance there as well. I was just thinking there's probably actually a whole bunch of these games that could be RL games, without too much trouble. Famous last words, of course. There is a game in here called, we'll get to it any second now. I hope, come on. I know this must be massively exciting for everyone. Nearly there. Chase, here it is. So it is, basically the idea is that you've got a sort of like a 20 by 20 grid. There are a bunch of robots in there. There's a bunch of zappers in there, and you are an agent in the middle of it. And the idea is it gets randomly started up, and then you have to move, and the robots will try and close in on you. The robots are not very smart, so they will basically walk into a zapper rather than actually move around a zapper. So the goal of the program, or the goal of the game, is to try and interpose a zapper between you and the robot, and to get rid of all the other 5 robots. This I felt was a little bit different from your standard toy text kind of challenges, because a lot of them are about find a goal. So frozen lake, get from one spot to another. Taxi, get from where you are, pick up a thing, get to another one. This one, the goal is actually stay away from everyone, and at the same time, actually interpose something that will get rid of them. So you're actually,
do you get points? Is there a score to the game?
There is no score in the game in the way it's written. It just says you win or you don't win. So that's sort of... And
winning means that...
you survive.
You survive and
well, that's
eliminate all the
it.
robots.
That's the only reward.
That's it. And this is, these were 1980 games.
Yeah.
So just to let you know...
No, but I mean, like, in terms
that's
of
a
the
spice
environment,
reward.
that's all that you're getting, right?
My first computer I owned had no... it only had memory. It had no hard drive. You had a language cassette that you would plug in and load. And so you'd write a game, and then you would turn your computer off, and that was it. It was gone.
Cool.
So that's a long time ago. I was pretty wrapped when I got my first hard drive, which was all 20 meg.
Oh yeah, I had the same one.
So,
this big.
but anyway, we digress. Another day. So I've got to the point where I have actually managed to get basically coded up the game, and I've got to a point where I can actually run it. Hoping I can run it. There we are. So it outputs a random start. So your action space is 9, because you can basically go 1, 2, 3, 4, 5, 6, 7, 8, 9, so around the clock. Or 5 is stay still, which if you've got a number pad, basically, which a lot of laptops don't, but it pretty much corresponds to 1 is southwest.
I don't get it.
So you can move. So in other words, I will move.
I'm not very good at counting, I think, but so how many, do I do king moves?
So king moves.
Yeah.
Okay.
Yeah, with the option to stay still as 5.
Yeah.
So
Oh, right.
So
Yeah, I
1,
see.
2, 3. So 3 will kill us. Because 3 will take us into a zapper, which I will just demonstrate. So there we are.
So X is a zapper.
Yeah, X is a zapper, R is a robot,
And we're A.
and we're the A for agent.
Right.
So originally it was P for player, but I put A for agent because then it's more R out. So there we are. So we've just managed to lose the first game. As you can see, it says agent eliminated, total reward of 0. Okay. So let's actually. Why are you doing that? It's working fine. This is why I normally do this at home on my other one. Let's see if that works. As you can see, I am learning lots about this kind of stuff.
So it's telling you that it cannot re-register the environment, so it's...
I
Yeah.
think the E was missing when you're selecting. The first letter of selection is missing.
Oh, okay. Yeah.
Yeah.
As usual, the tech never works on cue.
Shouldn't it have some kind of reset method? Don't
It should, yeah, okay, yep, there is a reset method. It's called restart the kernel.
That seems to be the long way around though.
It does, yeah, okay. We're gonna, why are you doing that? There is, this, sorry, I know why. It's because one of my files here, this one, I was making notes during the apologies. Right. Okay, there we are. Let's come back here. So now it's decided to work. Okay, so now we are not going to suicide into the zapper. What we're going to do is going to try and entice a robot into the zapper. So if we move down, which is 1, 2, so we go 2, we go down, and you'll see that we've moved down, and all the robots have tried to move one closer to us. So if we move down again, we managed to eliminate one of the robots, and you see we got a reward of 1.
So it does reward.
Yeah,
Okay.
so you get.
It's like one score.
Originally, the game just said win or lose, but I thought maybe we'll get it a little bit less sparse.
Yeah.
You know, every robot you eliminate, you get 1 point. So okay, so let's move. Say, so we've got another. So this other robot's kind of closing in on us. So what we can do? Let's hide it. We can go. Let's go across that way. Which would be
If you
1,
went
2,
down
3,
now,
4.
would that also be a zapper, or would that
Yes.
just be a...
So if you go down,
yeah.
it kills you. So
Okay.
you can't. So let's scoot along the bottom, and so the robots will always try and take the step that will close the gap the quickest. So that means that, you know, in that case, it basically felt that was the quickest way to get to the agent.
Can the robots collide in each other?
No. So and that leads to a problem which I'll get to in a moment. So if 2 robots, so the robots are numbered 1 to 5. So if robot 1 moves and robot 2 wants to try and get to where robot 1 is, or to get to the agent, it will not move.
No, cool.
So it will say, no, I can't move into that space. That's actually going to lead to one of the questions that I have. So, so that's pretty much, you know, it's not much more complex than that. We've managed to get rid of that one. So let's move. So 1, 2, 3, 4, 5, 6, 7. So let's move. Okay, we don't want to run into that, so we'll move across. I typed in 74. Okay, we'll move there, and now I can actually just sit here, and they will suicide on the thing, and we win because we eliminated all 5. There we are.
Cool.
This should be it should be pretty simple as far as a problem goes from RL, because it's a toy text. Action space, n equals 9. Pretty easy. But state space is where in the last 2 days I've come a real cropper. For a couple of reasons. So,
so your problem is not to incorporate. What's your problem?
So-
I remember you
Not
saying
the environment, it's the actual
Is it the actual-
so in OpenAI, if I understand what they're doing with their discrete environment, is they're basically saying we're not going to calculate this on the fly because it's a finite Markov decision process (MDP). You can actually pre-calculate everything, and then it's just a lookup table. Effectively, that's my understanding of how they're doing it correctly. So,
You mean like this?
So if you look
the
at
implementation of the.
But you don't have to follow these instructions, right? All you
No.
need to is just to provide an interface, right?
Yeah.
Step, your words,
Yeah.
blah 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 blah
Yeah.
blah.
so if you look at this, and this is again where it's going out onto the edge of my Python skills as well. This is Frozen Lake setup, which is a 4x4 matrix. And what they do is that they calculate they basically say, right, we've got 4, sorry, this isn't so exciting for those on the internet, but they got 4 actions, so north, right, north, east, west and south. The number of states is 16, so they enumerate the states to be 1 to 16.
Yeah.
So they don't give, and this comes to the question of, should I feed back the array of the actual, this set up here, or should I, because the other thing, originally I basically unraveled it into a 1D vector, and then I thought, no, maybe I shouldn't do that because it should be the person who's programming the agent to determine how they want to treat the environment information coming back to them. I shouldn't assume that they want it as a 1D vector.
No, it's you who decided.
yeah, that's what we found.
The one who creates environment decides what's the state, what the state looks
The
like.
state representation.
Yeah.
Okay.
The best suggestion probably is just to unravel it into one that just make it flat, because that's what every
No.
with the state
Not
observation
in this-
space.
Yeah. But
It's,
not,
so it's
not
not just pixels, right? Or you want to
Yeah,
treat them
they
as
are
pixels.
pixels.
You want to treat them as pixels.
Yes.
You could do it as a
But it doesn't
3D
matter. It
as a
doesn't matter at all.
three-dimensional image.
Like
or a
at all.
three-dimensional
Can I tell
image.
you-
It's up to you completely.
I can tell you what I've done for the Connect 4, which is very similar to here.
That's what I was.
So it's basically, I also just kind of stumbled into it because I just didn't think about it before I ran into exactly this problem.
Yeah.
So basically what I did was just just create pixels. So every cell has a couple of values. So let's say empty is 0, and you've got this would be 1, and you've got your agent would be 2, and then a robot would be 3. So you would just create like a uint array.
Well, this is
20 by 20.
Yeah. So which
I think
is
That's like the easiest way.
And wasn't in this AlphaGo zeros, they had like a separate layer for each of the.
Yeah, I was just
Okay,
going to say
right.
this is
So-
magic numbers, right? If you did it in a 3-dimensional image or with a 20 by 3 matrix, then you would have like one hot encoded, I guess,
Yeah.
Right.
positions for each.
Yeah.
Oh, sorry, 20 by 4.
So you can
Sorry.
so in the end actually what
Sorry,
I
200 by 4.
so this
400 by 4.
this is the representation that I use
Sorry.
internally in the environment.
Yeah.
And the thing that I return, so the S that the step returns, it's actually a stack of zeros and ones.
Yeah, exactly.
So
yeah.
and in this case so 0 you don't need, so you have a layer for this,
Yeah.
and for this.
That's exactly what JD did. Remember the star eating alien example that Patrick demonstrated on JavaScript? That's exactly how it
because internally this is just a human-friendly version.
Oh,
Or that's how it's
exactly.
stored internally.
Yeah.
But what you're saying is you just one hot it effectively.
Yeah.
So we have exactly the same
Yeah.
Oh, not quite. I've got
yeah.
I've got
X's are 2s, but yeah.
agent is 4.
Yeah.
So zappers, I've got 0 is empty. Zapper is 1,
is boundary.
but I've made a difference between the boundary zappers
Yeah.
and the internal zappers.
Okay.
Why I did that, not sure, but I'm thinking that maybe the agent might want to know the difference between a boundary zapper and an internal zapper, because as each episode evolves, these ones always stay in the same place.
Yeah.
The other ones will move. because so this is where
You could make it easier or harder by changing that. Like, if they're all just the same zapper, like you have to learn the better ones don't move anyway.
so if you were using the same arena every time, so if I was using the same seed to generate that, then I think this would probably be a deterministic problem, because it's basically there is a solution that will work every time.
Yeah.
There is no random element to it
Yeah.
at that point.
Yeah.
You introduce, because the robots always move in a completely predictable manner.
Yeah.
So the randomness comes from having multiple episodes with a different seed to build a different grid.
Yeah.
So you could do it that way.
Yeah.
There are other things that go into it, but for a simple kind of, let's make it a bit challenging,
Yeah.
you can do that. And then I've got code at home which I haven't put up yet at the moment, which you can feed the random seed into the episode. So if you want the same one again and again and again and again, you just leave it set to 0.
Yeah.
If you want to have a different field every time, you just use the episode number, for example.
Yeah. Yeah.
But so this is all good. Where I get into trouble with this is this here. So what is the number of states? Because originally I just thought, well, this is never changing, so, and this is where I start running into math problems.
This is combinatorics.
Yeah. I thought, oh, well, it's just going to be, that's effectively 18 by 18, and then there's going to be, so you can place 10 of these, so it's going to be 10, what is it, 10 times 9 times 8 times 7.
It's astronomical. Like it's irrelevant.
Yeah.
It's way too much.
Yeah. Well, I was originally thinking it might only be 5,000 or maybe 16,000, and then other things started occurring.
No, because look at how many choices you have.
Yeah.
So it's basically just the axis is 20 choose 10. If I see.
There's 10.
Yeah.
Sorry, there's
So
10 X's.
20 choose 10.
And 384.
384 choose 10.
Choose
now.
10.
Yeah.
Yeah.
Okay.
So.
Hang on, I have Wolfram Alpha.
So
it feels like, yes, there probably is a finite number of states, but it's going to be very large.
I mean, one-hot coding makes absolutely, there's no information in that.
Yeah.
Because you're not ever going to see exactly that same pattern again, unless you're just, it's not very likely anyway. You're not going to learn anything generalizable by encoding it that way.
Yeah. So the number of states just by that is 1.707 times 10 to the 19. That's enough states.
Yeah, and then so
and you haven't put a single robot in
you
yet.
multiply that by whatever is left after you do that choosing. So 3 something.
But why would you compute it?
Yeah, exactly. You don't have to.
Yeah, but because the OpenAI examples, they actually do compute the actual state, the numbers of states. If you look at
But that's because Frozen Lake and stuff
Yeah.
uses lookup tables.
Yeah.
Just don't use a lookup table.
that's right, exactly. So that was, this is where I was running. Originally I was thinking I don't need to do a lookup table, and then I started looking through the OpenAI code and went, oh, wait a second, I do need to do this. So now I need to calculate the number of states.
Yeah.
And then I basically got into all sorts of trouble because my math isn't that good.
But I think that's when they do that for Frozen Lake. They do that so that you can lazily, for your lookup table in the agent, use the number of states given by the game. You don't have to do that if you
No,
make
it's
it
not
run.
even that. It's not even that. It's just like the state in Frozen Lake. It's like, what is it? Like 4 by 4.
It's 4 by 4,
Yeah,
it's a
exactly.
standard.
Yeah.
And the state is what cell are you in?
Yes.
Yeah, exactly.
So
It's
it's
six-
just like
that's
obviously
it.
that you could just
Yeah.
take 1 out of
That's
16.
Yeah.
So but here the state is much richer. Like
Yeah.
astronomically more richer.
Yeah.
So I think it's so this I think is a more realistic way, and it's also something that you could immediately feed into a convolutional neural net.
Yes.
So it makes everything much easier.
Yeah.
Okay, cool. Great. Excellent. Because so I was starting to get
And just
worried.
to on that neural net, on that convolutional network, don't max pool.
Right.
Oh,
As we
yeah.
had to figure out.
Let me get it up and running before you even go to that.
Yeah.
So, because then one of the example DQNs that I've seen, which like Keras-based ones, plugged into Cartpole, another very simple AI, actually does need the number of states So maybe I'll come back next week with the next round of problems. But I do have one other challenge, which is to do with the representation of the end state, the terminal state.
Yeah.
And it might be best if I draw this out. So, because if you have a situation where you have like a zapper and you have your agent, so basically, so then you go, right, I move the agent into the zapper.
Yeah.
So ends the episode.
Yeah.
But at that point, what should I feed back to the agent? Should I feed back that, as in the agent has disappeared? Or should I feed back, well, that's the position it was in and the episode ended? Because done will be coming back as
It
true.
doesn't really matter. Because what you want to, so it's either is fine. Even if you put all x's everywhere as your terminal state, it wouldn't matter. The reason is that the choice, the moment in which the representation of your state is important is just before you do that. That's the moment that your state representation is actually important.
Okay.
And after that, like, so basically what you're,
So it's going to discount the next state when it gets the done flag back? So
yeah, exactly.
Yeah.
So this is, so the, so sometimes they write it as I, which is sort of one of two, or maybe IN, which is like one of two values, is gamma to the n if you end step bootstrapping. If we just do T0 is just n is 1. And it's, so this is if the next state is not terminal, and this is if the next state is terminal. So then if you, so this is just an indicator basically. And then what you can use that for is you can say, okay, the observation that I have right now, so this is the sort of this situation that you're in. So this, if you use TD learning, you would just have basically plus I n times whatever the next. If that makes any sense. Does this make sense? So basically, you don't really care what this state representation is in the terminal state because this guy will be 0. So you never actually have to evaluate it. You can evaluate it, but the value itself will never actually be used, so it doesn't really matter. So what I often do is I just put like some bogus state in there.
Okay. So it's not going to evaluate the next state, but it still takes on the reward you get for...
Yeah.
But yeah, it's your job to specify the reward.
Yeah.
Because this leads to another question I have around end states, which is...
I'm just going to remove this whole...
So if we have the situation where we have the agent here and we have a robot here, and the agent moves onto there, dying, but at the same time, so should the episode end then, or does should the robot actually move to where the agent is, and then the episode ends?
That depends on your environment. Because if you imagine your robots like reacting to where you are, then you would die before the robot does anything.
Yeah, because it feels, because the action of the agent and the robot is the step. So ending halfway through a step feels wrong. I don't have a mathematical reason for that, I just think it feels wrong.
The
You
way I
win
see
the
it,
game,
I see
according
it
to
as
the
two
game. You
steps.
win the game.
Yeah.
But just go by the rules.
Yeah, is it like 2-player?
Yeah.
Like, so you move and then the robots move, or
Yeah.
the robots move first. Like
That's
someone has to
semantic,
move
yeah.
first.
Okay,
It's
so
like
you
two
have
steps
to-
under the hood, but then not really.
Yeah. Okay, so you have to say whether it's 2 players, you take it in turns.
Yeah.
Well, actually,
But you
you
don't
must
have
have
to-
implemented this already, actually.
So
So
I have made a decision on what I do in this case.
Well,
but I'm bringing it up here to see what
even
you guys think.
Even if you didn't know this, you would have already have to implement this, because you had to implement where does R go?
Yeah.
Does it go in the
this
before state or
position
the after
after
state?
Yeah.
Well, it goes to the after state.
Yeah. Well, then
because as I said, I just felt it was wrong to end the episode halfway through this step.
Yeah.
And so, but if you're saying, well, hey, you can make your own rules, so it doesn't really matter. You know, the agent will just need to learn. Because what happens, you end up with that situation that if is that you get so doing this, you still get reward +1. So sorry,
No.
you still get reward equals 1, even though you died. So if the agent had moved that way,
No, that,
Well, that's
No.
that's not a thing.
No.
That feels wrong.
I see it the other way around actually. Where so because you move first before the robot moves, you die before the robot ever does anything.
yeah, but the step. So the step is the actions of the agent plus the robots. The agent gets 0 reward
Right.
until a robot throws itself in the zapper.
I would see the step. So each step would be have point A and point B.
Yeah.
Point A is update
Agent?
A,
Yeah.
and then step B, B of the same step.
Yeah.
That would be update R's, all the
Yeah.
R's.
Yeah.
Yep.
So then, now if you end up in a terminal state here, I would just so this never happens.
Yeah.
So then the
Yeah.
state also isn't updated in terms of where the robots are.
Yeah. The robot might kill itself, but since you have the done flag already, the update doesn't
But
get through.
The thing is, the done flag is not given until here.
Yeah, but that's up to you.
Yeah. Yeah.
I
Okay.
mean,
So it's my
you could
choice.
just-
Yeah.
Because basically you can bail out of the step saying if I'm dead, then return.
Yeah.
the die.
Return.
Yeah.
And which then solves, actually is an alternative solution to the next problem I was going to propose, which is you have this situation where the agent, if it does get the reward for killing the robot, even though it's died, it's a Pyrrhic victory. The thing is, it's equal in value to if it had moved away and the robot had tried to kill it. So it actually, the agent gets there's no difference for the agent whether it lives or dies. And I'm thinking that, you could make that part of the ruels, but I think
Wait,
that would be better.
I didn't follow. Sorry.
Okay, so if we have the situation, so if the agent's turn to move, it moves into the zapper,
Yeah.
but the robot said, well, that's where the agent is, the ghost of the agent, or the agent
Yeah.
frying on the zapper.
Yeah.
So I would try and move into it as well.
Yeah.
But if the other thing the agent could have done is the agent could have said, well, actually, I'll just stay where I am.
Yeah.
The robot goes in. Either way, agent gets 1 reward for killing a robot, even though the agent's dead.
Right. So
Well-
this is in the hypothetical case that you don't break out of the.
Yeah. So that's why. But the thing is that
it's the same.
this would actually would
Because-
actually get the same result. I
No,
think.
No.
Sorry, the
No,
solution.
it's
Sorry,
break
my
out.
bad. The solution is the same because in both cases you have to formulate a stochastic policy. That's the solution that I think. Because
No, not necessarily. It can
oh
be-
no. Because if let's say the condition is that A has to be not done to get the reward, then your policy would be 50-50 going this way or remaining here. Yeah. But if you can martyr yourself or whatever you want to call it, then you have a 1/3 this way stay or go that way policy. So either way, you have to implement stochastic policy.
Yeah,
but this is regardless of the policy, right? Like this is just like.
Oh, what was it? Sorry.
Can I make like
Yes.
a simple suggestion that
Fine.
might
Fine.
fix most of these problems? Probably you should just shape your reward a little bit. For example, the typical solution would be if you kill a robot, you get +100. If you die, you get -100. And if you survive for 1 step, you get +1 reward. That's it. You survive as long as you can, and you get a huge benefit of killing other robots.
Yeah.
And
Yeah.
But that's not sparse reward. That's way easier. Why would you do that?
No,
Change
I
the
would-
reward.
I would only
So
do
that's-
this
that's-
once.
that's-
You can still keep
Yeah,
it
it's-
fixed.
Yeah.
and then
That's a good idea.
and then you
Yeah,
just
change the
Yeah,
reward.
that's
Cheat.
Actually, no,
That's
you're
not-
right.
that's
You're
not
right. You
cheating.
could just
That's
you could solve this, and then you could still solve it for less and less generous rewards, right?
Yeah, because
You
that will-
apply
that will-
different
yeah,
update
yeah.
mechanisms.
Actually, no. Wouldn't
I
that
don't like it.
wouldn't that
You could
encourage
use-
the agent to try and keep the game going as long as possible?
If you didn't want it to keep just like getting a reward every time, so you can just give it a massive reward, negative reward for dying. And it would,
Yeah.
like,
but
inject
it's
the same
sparse,
sort of
so
thing.
that's not good.
But it would still like realised that it got like,
I mean,
like a negative 100 or something.
well, if you don't give a reward for survival thing, you may collapse to the situation when your agent learns that anyway, I'm gonna die anyway.
Oh yeah.
Yes.
Well, why keep trying?
Yeah.
No, because sometimes it recognizes that a robot goes into his app, right?
Yeah.
Mm.
Because it's not getting negative every time step.
No.
It's just getting negative when it dies, so it knows it figures out not to die.
Yeah.
Not
And
to
and so the hard thing, so the very sparse version, which is you win plus 1 point if you win, that's too hard. Like that's because the chance of you just stumbling upon that just by chance is definitely
Well, yeah,
just out of the
but
question.
that's what I'm saying. I'm just trying to help to make the
No, but that's the thing. No, but like
So
you
these
know,
people were-
for a robot to walk into
I
a zapper,
remember-
that can happen just by chance. And then when stuff happens that you want to happen, when it just happens by chance, then you're off the races basically, right?
And I think with the high
That's
reward,
basically what it
You
is.
could do
like
both. I think you could do
Yeah.
both because you could start with. Sorry, the next quick thing. You could start with the generous rewards, and you could use a really safe. Like just use your catalog of update mechanisms and use a safe one. And then once you made it work, just so, fail fast kind of thing. Make it work. Make a soapbox racer, right? With like really shoddy wheels, just so it can roll down the hill to start with. And then once you've got that working and you know that your entire environment just does what you want it to do, then you grab another from the Keras-Gym package, another update mechanism, make it more complicated, make the rewards more sparse. Yeah? And then just
Because unfortunately I have to go. That's what I'm going to implement. So agent dies -1, robot dies +1.
Agent dies -100.
Yeah.
Robot dies +100.
What? Why is that? They're the same,
And,
aren't they?
and if agent survives for one step, at each time step, he gets +1 reward.
I don't think that's a good idea
That's
because
definitely-
if the agent could actually have a situation where it just goes like this and the robot goes around like this, that means effectively it can have infinite reward.
Yeah, but don't you have a limit? Time limit?
No, I do. That was one of my questions.
Ah,
Should
you
I
should
have
have.
a
You
set
should.
limit?
You should have one, yeah.
Okay.
It's just a different problem now.
Yeah.
Do that.
They work
I'm
together,
definitely
but
not in
yeah.
favor of. I'm in favor of only giving a reward if a robot dies.
Well,
That's it.
look, it's probably only
Yeah.
about 3 or 4
It's
lines of
harder.
code
It's
different.
harder, but it's
so
it's
why don't I
possible.
try?
Like,
Why don't I
it's
try both and see what we get?
It's like super easy. Like you just it's
If
like
you could
2
figure
layers
out-
of
if you could
CNN.
I mean, I would do this one, and then
graph.
I would just make
Yeah,
a
like
harder
which
version
does
of
which,
it,
that would be
with
really
the
interesting, especially
-1
considering
for
which
time,
which
+1 for reading.
agent sort of
Isn't it like a
algorithm and so on you
goal
choose. That would be really, really
complexity
cool.
type of problem?
Yeah.
You also want to look at
Final goal
look at
of
something
this
about
distribution
Dyna
stuff
Plus.
with the
Yeah.
Because they do a
No,
similar
that-
thing where you explore.
the biggest
No, but they
more.
go, no.
This
So
might be
just because it's
especially
20 by 20
valuable
doesn't mean
for
that it's
when
as hard as
you're,
go.
but
when
it's
you're
similar in
zapping stuff
nature
around.
and probably
Because with Dyna and Dyna Plus, your
I think
agent will
with
keep
just like
you'll keep in
so
mind
my
where it
guess
hasn't
is-
been for a while.
Yeah.
So if
So I'll mark my
if
words.
the zappers have moved, it'll go back
You
there.
take
and
Because it doesn't
two
seem
layers
like
of
stay there.
The zappers.
2 layers
the
of
intention of the zappers
convolutions
won't be
and then
downloaded.
Yeah,
Just
one
the
layer
code.
of dense.
Yeah.
Okay, because I suspect
think
that
we'll
that's
just
going
solve
to
this.
cause the agent to try
Okay.
and
I think,
make the episode
It
as
is
long
like
as
you get
possible.
punished for
But
making
hey, that's a
bad moves
hypothesis,
early
and we
on.
can
No,
test
that's
it.
true, that's
You
true,
could
that's
say-
true, but if you have a time limit.
Yeah, give it 500 steps.
Oh, okay.
Yeah,
It's possible
we've got
to
it.
put
You make
2 levels
bad
of the
moves, you get
reward.
hurt.
For example,
Yeah.
if the robot is killed, +1, and if the agent survives, another +1, or 2, or the reward of 2. And if only the agent survived and the robot survived, only 1. And it's possible to 2 levels of the reward.
Yeah, I mean you can do anything, right?
Yeah, because I think that is a problem. when
As
the
per,
agent, another question is how to solve it. The reward is 10 to infinity.
actually
Give it both. Give it a time limit and the sparse reward. That should be the most interesting, I think.
Yeah, well, that's.
Because otherwise, if you have it infinite
no, it's like
Let
Chris
next one,
said,
next
it's
one.
only reward is for time survival of the agent, and then the maybe negative reward, and then the shorter the episode,
Oh,
and
that's
no
cool.
rewards for robots dying.
Yeah,
And
that
then
is
just the
cool.
time the shorter you kill.
Wait,
all the
No, that
robots.
wouldn't work because then the agent would just throw itself into it.
Oh, no, the agent dying would have to. The agent dying would have to give it more than the
Can't believe
time
what I'm
limit.
hearing.
Sorry.
Anyways, I did have one last question, which is there are some initial states where basically the agent cannot win. So, in other words, like agent is, it's just equally likely that that's the initial state. Basically, you're dead.
Yeah.
There are two ways I can see to solve this. One is easy, one is hard. The hard one is somehow you exclude the initial states where it cannot win, and I don't know how to do that. That's the hard way. The easy way
But isn't
is...
this environment taking care of that?
No, just leave
No.
it. Let it be.
Yeah.
Well,
I would just let it be.
that's
Yeah.
option two.
Yeah.
In the original
Same as
1980s game, you could hit space and it would randomly pick you up and drop you somewhere else on the board.
Like a jump?
But yeah, it's like it's massive.
Random jump.
That's
Random
really
jump.
interesting.
That's cool.
I would definitely implement that as an action.
Yeah, it's actually terrible.
So that would
but
be
it'll constantly
action
do
two.
that.
Yeah, well,
But-
maybe.
Well,
Maybe.
Oh, does it have a limited? Does it have?
No,
limited?
it doesn't. It just, but it also means that
You
the
could
agent-
land on a robot.
you can land on a robot, you can land on a
Yeah,
zapper.
Oh,
And then you can do
Yeah.
this.
Yeah.
interesting.
So that was that, and that does add a more random element
Yeah.
to the
I wouldn't,
game.
honestly,
Yeah.
I wouldn't do that because right now your game isn't random. Initial
Yeah.
state is random, but it's MDP.
Yeah.
It's deterministic.
Ah.
And if you hit the space and you randomly jump somewhere, then your process becomes stochastic, and you can't model it with the typical DQN and stuff. You would need to feed several states from the past to your critic or whatever network it is or whatever it is.
Really? Because your state
Just to catch. Even if you do it, doesn't help you, right?
But it's
Yeah,
like,
it's
it doesn't
a
make
benefit,
it
it's
a
a
non
benefit.
It doesn't
right?
exactly
It's
because your state is
still
still dependent on. It's basically the start of a new episode. Yeah. So.
Well, no, it's not, because there won't necessarily be 5 robots to begin with, because you might have eliminated some along the way.
No, but
Yeah,
it's,
but in
it's still
principle,
an
the
MVP, right?
state
Because you'll have all
is
the
still
information.
finite in the sense that it's
But the
determined
transition, what's the probability of the
it's
transition?
not because
it's
it's
uniform
of
operation.
Is it?
to
Yeah.
be determined.
Or whatever
Okay.
you decide it to be. right?
Okay, so it sounds like I have 3 tasks to do. One is to get this up and running, just basically ignoring trying to calculate the states, just say, your problem, here's the state, do what you want with
Yeah.
it.
Absolutely.
Yeah.
And one hotting is another option to make
Yeah.
it for them to do.
I would do
although-
like the stacking
Yeah.
of the
Mhm.
one
Yeah.
hot.
Yeah.
So that's task 1, and then so task 2 is actually then plug in some, for me to actually try and do some simple DQN and make it work.
Yeah.
Number 2 is play with the different reward algorithms, and number 3 is maybe implement the jumping. But in the
Yeah.
first case, if you start in that position where you're dead, tough bickies for the moment.
Well, if you don't care about the agent, about your computer to get frustrated because of this, but you probably not.
Yeah.
So
Yeah.
just
Yeah.
Well, one of the things I have on my own to-do list is to actually play through the first 100 games and actually record them, and that way I can actually, and so that way I've
Oh, you
got,
want to build a repo buffer?
I
for
can
that?
actually, you could do that. I don't think
Yeah.
you need to. This is not AlphaGo.
Close.
But it's 20 by 20, yeah, that's right.
One question.
Yeah.
You can do the random jumping in the middle of the game.
You can do it as a move at any time. You don't have to be in a no-lose position to do it, but obviously you can lose very quickly if you do it.
Yeah.
Anyway, so okay. So I got some stuff. So mission successful. I have created. It's not a.
No,
it's
it's
actually
really
been an
interesting.
interesting conversation.
Yeah, it's
and
cool.
challenging.
No,
stuff.
that's cool.
Thanks
So,
for sharing.
Yeah.
No worries. And I'll get to it. The repo, I'll post it on the Slack if you really want to see my horrible coding.
Oh, no, it'll be interesting to see. Absolutely.
Yeah.
And we'll see where we go. And I've already written some code to output to PNG, so I might be able to make some videos of gameplay as well.
And your Chaos Gym link is on the Slack channel as well, right?
Yeah, I think you have to scroll up a little bit.
I'm not sure
I
how
think
useful it
I
might
read
be,
the
but-
entire Slack channel from
Yeah.
whenever it started, so
Yeah.
you've seen some of the other stuff.
Yeah.
So
Yeah.
Anyway, thank you very much, everyone.
Oh, you're most welcome. Thanks for showing us.
That's really cool.
I wonder what the person on the internet thinks.
Yeah.
If you have a
The one
comment or a good idea.
Oops, I'm going to stop presenting, otherwise it...
Other than that, switch on next time. Have a great weekend or whatever. Thanks for watching.